Welcome to today's paper reading. Today's paper is titled, World Model on Million-Length Video and Language with Blockwise RingAttention. This paper was published on the AR14 preprint by Hao Liu and colleagues from UC Berkeley. The abstract highlights the limitations of current language models, particularly their difficulty with complex, long-form tasks and understanding aspects of the world not easily described in words. It emphasizes the value of video sequences for providing temporal information that is absent in language and static images, suggesting that joint modeling of video and language could enhance AI capabilities. The paper addresses significant challenges such as memory constraints, computational complexity, and limited datasets by curating a large dataset, employing advanced techniques like Blockwise RingAttention, and gradually increasing context size. Key contributions include training one of the largest context size transformers, providing solutions for vision-language training challenges, and open sourcing a family of models capable of processing long sequences of text and video. Figure 1 demonstrates LWM's capability to answer questions over a 1-hour YouTube video compilation, consisting of over 500 video clips. This qualitative comparison highlights LWM Chat 1M's superior performance against models like Gemini Pro Vision, GPT-4v, and other open-source models. The figure showcases LWM's ability to understand and respond to questions that require detailed comprehension of long video content. Figure 2 demonstrates the capability of LWM to retrieve facts accurately across a context length of up to 1 million tokens. The figure compares the performance of LWM in needle retrieval tasks against Gemini Pro and GPT-4, highlighting that LWM can extend its context length up to 8 times longer than these models. The x-axis of the figure is scaled to show fine-grained results, using a logarithmic scale from 0 to 128K and a linear scale from 128K to 1M. This comparison underscores LWM's competitive performance in handling extended context lengths, which is crucial for tasks requiring deep understanding and accurate retrieval of information from extensive data sets. The current approaches to modeling the world are limited to short sequences of language or short sequences of images and videos. This results in models that lack understanding of parts of the world that are hard to represent in text or short clips, and are unable to process complex long-form language and visual tasks. Temporal structure in video sequences provides helpful information that is missing from language or far less obvious in static images and short clips. Long language sequences encode information that short sequences cannot, crucial for various applications such as long document retrieval or coding. Long videos provide a rich context that short clips cannot grasp, showing how scenes connect, the development of events, and the cause and effect of actions within the temporal dimension of the video. However, modeling millions of tokens is extremely difficult due to high memory costs, computational complexity, and lack of suitable datasets. The paper introduces a large autoregressive transformer model with an extensive context window of up to 1 million tokens. This model builds upon the Llama 2 7B architecture. To achieve this, the authors employ several strategies, including extending the context to 1 million tokens using books, as detailed in Section 3. Additionally, the model undergoes joint training on long multimodal sequences, which include text-image and text-video data, further enhancing its capabilities. The training stages and datasets are visually represented in Figure 3, while the model architecture is depicted in Figure 4. The first stage of training, focusing on long context language models, is particularly emphasized and is discussed in depth in Section 3. In this stage, the authors develop 2 long context language models, LWM Text and LWM Text Chat. These models are trained using RingAttention and Blockwise Transformer, with modifications to positional encoding to handle longer sequences. The training process involves progressively increasing the sequence length, starting from 32K tokens and ending at 1M tokens. This approach allows the model to learn shorter-range dependencies before tackling longer sequences, thereby saving computational resources. Additionally, the authors construct curate data by chunking documents from the book's 3 dataset and generating question-answer pairs, which are then concatenated to form long context examples for training. Figure 3 outlines the multimodal training process of a large world model. The first stage, LLM context extension, involves expanding the context size using the book's 3 dataset, starting from 32K tokens and reaching up to 1M tokens. The second stage, vision language training, focuses on training the model on visual and video content of different lengths. The pie chart in the figure shows the distribution of 495B tokens across images, short and long videos, and 33B tokens of text data. The lower panel demonstrates the model's interactive capabilities in understanding and responding to queries about complex multimodal scenarios. Figure 4 illustrates the architecture of the Large World Model, LWM, which is an autoregressive transformer designed to handle sequences of millions of tokens. Each frame in a video is tokenized using VKGN into 256 tokens, which are then concatenated with text tokens and fed into transformers to predict the next token in an autoregressive manner. The model is trained to handle various data formats, including image text, text image, video, text video, and purely text formats. To distinguish between image and text tokens, and for decoding purposes, special delimiters such as vision, EOF, and EVE are used to mark the end of frames and modalities. These delimiters help in managing the different types of input data and ensuring the model can handle multimodal sequences effectively. Figure 5 illustrates the performance of our LWM TextChat 1M model in the needle retrieval task. The model achieves near-perfect accuracy across various positions within a 1M context window, demonstrating its robust capability in retrieving specific information from extensive text data. Figure 6 illustrates the performance of the LWM-1M model in a multi-needle retrieval task. The key variables are N, representing the total number of facts in the context, and R, the number of specific facts the model is tasked to retrieve. The figure showcases how the model's accuracy varies with different combinations of N and R, highlighting its ability to generalize well when retrieving a single needle from multiple options, with a slight decline in performance when more than one needle needs to be retrieved. Table 1 provides detailed information about the training stages of the LWM text model, including sequence length, rope theta scaling, tokens per batch, total tokens processed, wall clock time, and compute resources used. Each stage progressively increases the effective context length of the model, starting from 32K and extending to 1M. The table highlights the scaling of rope theta with context length and the total tokens processed during each training stage, which are crucial for understanding the model's capacity and training efficiency. Table 2 provides detailed training specifications for the LWM TextChat models. Key points include the model parameters set at 7B, sequence lengths ranging from 128K to 1M, and a consistent total number of tokens at 1.2B across different sequence lengths. These details are crucial for understanding the training setup and performance of the models in long context chat fine-tuning. Table 3 presents a comparison of multi-needle retrieval accuracy across different models, including Gemini Pro, GPT-4, and LWM Text 1M, ours, under varying context lengths of 32K, 128K, and 1M tokens. The results indicate that our model performs competitively or better than GPT-4 in retrieving a single needle, with slight degradation when retrieving more than one needle. This table highlights the adaptability and performance of our model in different retrieval tasks, showcasing its potential for future advancements in longer context models. Table 4 provides a detailed comparison of the Llama 2-7B model with a 4K context against its context-expanded counterparts, ranging from 32K to 1M tokens. The evaluation covers various language tasks, showing that increasing the context size does not degrade performance on short context tasks. Instead, models with larger context capacities maintain or even improve their performance across these tasks. This suggests that context expansion does not hinder the model's ability to handle short context tasks effectively, highlighting their adaptability to different task requirements without compromising efficiency. Table 5 presents the empty bench scores for various context sizes, indicating a slight decline in conversational ability as context size increases. This decrease is attributed to less training on longer sequences. The data suggests that this performance could be enhanced with additional training on more extensive datasets. Table 6 illustrates the relationship between the mix of chat and fact retrieval tasks and their impact on MT-bench score and needle retrieval accuracy. As the proportion of chat tasks increases, the MT-bench score improves, indicating better chat performance. However, this comes at the cost of a decrease in needle retrieval accuracy, suggesting a trade-off where enhancing chat interaction capabilities may reduce the system's ability to accurately retrieve specific information. This trade-off is evident across different models and task mixes, highlighting the balance required between conversational ability and information retrieval precision. Table 7 details the training stages for LWM and LWM chat models. Each stage progressively increases the sequence length while maintaining the same parameter size of 7b. The sequence length starts at 210 and increases to 220. The total number of tokens decreases significantly from 363 billion in the initial stage to just 0.4 billion in the final stage. This table provides a clear view of the scaling process in training these models. In this stage, the authors focus on learning long-context vision language models. They introduce architectural modifications to incorporate vision input, such as using VQGN for tokenization and interleaving vision and text tokens with new boundary tokens. The training process involves progressive training on a mix of text, image, and video data, with attention to masking and reweighting losses. Evaluation results show the model's capabilities in long video understanding, image and short video understanding, and image and video generation. These results demonstrate the model's ability to handle long sequences and its potential for future improvements in vision language tasks. Figure 7 demonstrates the capability of LWM in answering questions about video content. The examples provided include a 3-minute video of animals and a 2-minute video of a man riding a bike down a trail. These examples showcase LWM's ability to understand and respond to queries about video details. More examples of LWM's video question answering capabilities can be found in Appendix B. Table 8 presents the performance benchmarks for image understanding across various methods. The table includes metrics for visual token, VQV2, GQA, VisWiz, SQA, TextVQA, POP, and MMBet. Key methods compared include MiniGPT-4, Otter, InstructLib, and LLVA 1.5, each with their respective scores. Our model, LWM, using VQGN tokens, shows specific scores in these benchmarks, indicating areas for improvement and potential in future VQ-based architectures. Table 9 presents the performance metrics of various methods on video understanding benchmarks. Key highlights include video chat achieving 70.7% accuracy on MSRVTTQA, LWM, hours, scoring 55.9% on MSVDQA, and video LLVA attaining 70% accuracy on TGIFQA. These results indicate the effectiveness of different models in video understanding tasks. Figure 8 demonstrates the capability of LWM to generate images and videos from text input. The process involves using classifier-free guidance on the logits for autoregressive sampling, similar to prior work. Examples of these generated images and videos are provided, with more detailed examples available in Appendix E and Appendix D. Table 10 presents an ablation study comparing the performance of standard and mass sequence packing mechanisms across 3 tasks, VQV2, SQA, and POP. The results indicate that mass sequence packing significantly improves performance over naive packing, highlighting its importance for tasks requiring accurate image understanding. The models were trained using TPUv4-1024, which is roughly equivalent to 450 A100 GPUs, with a batch size of 8 million. The training utilized techniques such as FSDP, Blockwise Transformer, and RingAttention for handling large contexts. Figure 9 illustrates the model flops utilization, MFU, across different training stages, showing high MFU even for very large context sizes. The training loss curves for language and vision language models are depicted in figures 10 and 11, respectively. For inference, the code was scaled to support sequences of up to 1 million tokens by implementing RingAttention for decoding. This requires a minimum of TPU v4-128 with a TPU mesh sharding of 32 tensor parallelism and 4 sequence parallelism. Inference is performed in pure single precision, with potential for further improvements through scalability techniques like quantization. Figure 9 illustrates the model flops utilization, MFU, during different training stages for LWM text and LWM/LWM chat. The blue bars represent the MFU during language training, while the orange bars indicate the MFU during vision language training. This figure highlights the efficient utilization of MFU across various sequence lengths, demonstrating the effectiveness of the training process even for large context sizes. Figure 10 presents the training loss curves for each stage of the LWM text models. The graph illustrates the progression of loss reduction across different training stages, providing insights into the efficiency and effectiveness of the training process for these models. The author's work is related to several efforts in extending language models' context windows, often using novel extrapolation methods to expand pre-trained positional encodings followed by fine-tuning on longer context data. A simple yet effective approach adopted by the authors involves gradually increasing theta and rho positional encodings along with the training context window sizes. Additionally, the authors reference research into architectures that do not model pairwise interaction, such as sparse attention and sliding window, and parallelization along the sequence dimension, which is crucial for large context training. The authors also mention the hybrid usage of tensor parallelism and sequence parallelism to reduce memory cost on a single device. Furthermore, the author's work is related to multimodal learning, including instruction tuning for language tasks and combining vision and language. The author's approach is autoregressive tokens in, tokens out, allowing for flexible modeling of diverse forms of image text, text image, text video, video text, and purely video, image, or text formats. Figure 11 presents the training loss curves for each stage of the LWM and LWM chat models. It is important to note that the losses are a combination of different modalities and may not be directly comparable across stages. A significant observation is the sharp peak in the middle of the 1K training stage, which is attributed to the incorporation of EOF and EOV tokens into the Vision codebook. In this paper, the authors address the challenge of combining language and video to improve model understanding. They employ RingAttention and Blockwise transformers to efficiently train on large datasets, achieving a 1M context size in their model, LWM. This context size is the largest to date and enables the model to handle complex tasks involving long sequences. However, the work has limitations, such as the use of an image tokenizer for videos, the need for additional modalities like audio, and the lack of high-quality video datasets. Future work aims to improve video tokenization, incorporate more modalities, and enhance the quality and quantity of video data. Thank you for watching.